So in the last video we characterized transverse waves, and at that time I mentioned that when we take a look at sound waves, which are longitudinal waves, that I'd say they're just like transverse waves except. So in that spirit, here we go. So just as a reminder, the sort of the hallmark of sound waves is that we have alternating compressions and rarefactions. So these areas would be areas where the air got compressed. And here, for instance, would be where the air is rarefied. As a little bit of foreshadowing for when you get to light, we can mark the direction of propagation like so by erecting a ray that's perpendicular to the wavefronts pointing in the direction of propagation. And physicists actually cleverly call this a ray. So they use the exact same term that mathematicians do. So if you remember, we looked earlier at a slab of air. And we said that what's happening is the waving is moving back and forth. So in a transverse wave, the waving was happening perpendicular to the direction of propagation. Here it's parallel and anti-parallel. So let's say this is the equilibrium position. In this case here, they'll be oscillating between two extrema. So we can say that this is A and this is minus A. And what we'll do is we'll note what the x coordinate is, and we'll take a look at delta x. And what this will be is what the current x coordinate is minus the equilibrium position for that slab of air. So if delta x is positive, it means that the slab of air is currently over to the right, and if it's negative, it means it's currently over to the left. And that's again all saying that we are propagating to the right. Alrighty then. So with that, it turns out that you can describe the wave mathematically basically exactly the same way. Instead of saying y of x and t, you would say delta x of x and t. And this would still be equal to a cosine of 2 pi x over lambda minus or plus t over the period. Or again, remember the minus sign means you're going to the right, plus sign means you're going to the left as far as the direction of propagation goes. So it's mathematically the same sign. In so since you represent mathematically the same way, you still say that the speed is equal to f lambda and so forth. Now for the except part. When you snap a wave on a string, you can only see it propagate along the length of the string. And you can see a transverse wave propagate in 2 dimensions. For instance, if you throw a pebble into a pond, you'll see the waves propagate out in circles along the surface of the pond. What's different is that with sound waves, especially if the frequency of the source is low, they can propagate out spherically. So we call this a spherical wave. And what physicists usually do when we think about things in 3D, we usually try not to bother drawing in 3D, because I'm not the only one with poor artistic skills. So instead, you look at this collection of nested circles, but what a physicist has done is they're drawing a cross section. So they've just taken a section right out of the center. So this dot right here is the source. It's currently emanating a crest. These are subsequent crests propagating along. And we say that these compressions are, displacement crests are shaped as spherical shells. So even though we look at it in a circle, when we visualize it, when we see something like this, we always visualize it as nested spheres. And what we think is that the crests are propagating out in all directions. Now there's a bit of an issue as frequencies get higher. The shape will be spherical-ish for reasons that we won't get into in this course, but the next one. The shape of the shape of what's emitting the sound does have some say in how much of a spherical section you have. However, a really good approximation to something producing spherical waves is the subwoofer in a stereo. So for most of what I'm thinking about, I'll be thinking about subwoofers. Now, one thing to notice here is that as you get farther out, if I look at the same chunk of wave, if I look at the same 1 meter here, here, and here, let's say, what I'll notice is that the curvature of the wavefront gets flatter and flatter. And so if I get sufficiently far enough away, I can do a bit of a cheat. The ultimate example would be, say, if I'm looking at light waves coming from the sun, it takes 8 minutes for light to get from the sun to here. So when you're that far away, the spherical wavefronts don't look very spherical anymore to your detector. And then you can approximate them as what we call plane waves, where it's just the subsequent wavefronts all look like planes. They're separated by one wavelength, just like they are here, and they propagate right along. So these are the two approximations that we tend to use the most. Now, what we're going to be interested in is trying to characterize how loud a sound wave is. And to first attempt to do that, we can sit and think about what's going to go into that. The sound wave is going to have to impinge on your eardrum. And when it impinges on your eardrum, it's going to have to do work on your eardrum. So it would be reasonable to define a quantity called the intensity, and we'll use capital I for that. So sorry that we're reusing the same letters, moment of inertia, but I don't think the two are ever going to show up in the same context. So it's the power delivered by a wavefront over the area. So remember, power is the work that wavefront can do as a function of time. This work it can do in per unit time. And so here's my direction of propagation out perpendicular to the wavefront. So this way we can say so much energy is delivered to your eardrum by taking the intensity of the wave, multiplying it by the area of your eardrum, and that is the rate at which energy is being delivered to your eardrum, or the rate at which work is being done on your eardrum in order for you to actually hear something. So that makes sense. And the units of this are going to be just watts per square meter. All right. So if we think about our spherical sound waves, so let's say I've got a subwoofer located right here. let's think about two different listening positions. Let's say this one here is at some radius r1. This one here is at some radius r2. Now the sound waves are going to be spherical. I should probably have moved the whole thing down a bit, so oops, let me do that. There we go. So there we go. Oops. R2. And so we'll go ahead and finish drawing our spherical. You know it's spherical because I told you it was. Wave fronts around there. Oh man, that R2 one is just awful. Let's try to do a little better. Oops, get rid of that one too. All right. Yeah, it's better. So anyway, these are spheres. You know it is because I labeled them. The big deal here is that at either of these listening positions, we can figure out the intensity because we know the area of the wavefront. So the intensity is going to be the power delivered by the source, and that power will be distributed over the entire wavefront. And I just have to divide by the area of the wave. Well, it's a sphere. The surface area of a sphere is 4 pi r squared. This gets called the inverse square law. So what it says is that if I double the distance, the intensity drops not by a factor of 2, but by a factor of 4. So let's just do that with numbers to make this nice and concrete. Let's say I am currently 5 meters away from a subwoofer. And I'm hearing some intensity I1. And now I want to know how far away should I be such that I2 is a quarter of I1. There we go. At first blush, this seems like an impossible problem because we don't know the power of the source, for instance, stuff like that. But then we remember that whenever you see problems where it looks like you haven't been provided with a lot of the information, that this could be an example of a scaling problem. So let's write out what the intensity at point 2 would be. That would be the power of the source over 4 pi r2 squared. Then we'll divide that by the intensity at point 1, as long as you write the same kind of expression for location 1. Well, looky there. The power of the source, which I never knew, cancels, leaving me with 1s, and the 4 pi's will cancel. Now I gotta be careful here. What I've got at the moment is 1 over r2 squared all over 1 over r1 squared. So probably be a good idea to rationalize this a bit, and you'll get r1 squared over r2 squared after you multiply numerator and denominator both by r1 squared to make this denominator go away. Then we can observe that that's r1 over r2 squared. Okay. So we can take the square root of both sides. This will give me that r1 over r2 is equal to the square root of I2 over I1. So finally my R2 cross multiplying would be the square root of I1 over I2 R1. But you say I never gave you the intensity either. But remember, I did at least give you that I2 is a quarter I1. So you can put that in there. It's I1, and we said that I2 is a quarter I1 R1. Hey, look at that. The I1s cancel as well. So now I got 1 over a quarter, which is 4. Take the square root of that, I get 2. So this is 2R1. So this is 2 times 5 meters is 10 meters. All right, now here's the tricky question. If you think about your experience listening to a stereo, if you stand near the subwoofer, let's say, let's make it a meter away, and then you walk back to 2 meters away, does it actually sound to your ear like it's a quarter as loud? Definitely not to my ear, and probably not to yours either. So although the intensity has indeed dropped by a factor of 4, we don't perceive it that way. So to get a better characterization of how humans actually perceive it, we have another quantity that gets called the sound intensity level. So this is different from the sound intensity, I. This is the sound intensity level. And this is based on just an empirically observing. You put people in soundproof rooms. You play different sound levels at them. You ask them different sound intensities at them. You ask them how many times louder did this sound compared to that, etc., etc. Do it over lots of people. And it turns out that the model that the biologists who've done this give us is that this is a lowercase Greek beta. Draw one like that. It turns out that this sound intensity level can be well fit to this empirical relationship. 10 decibels, I'll get into a decibel in a second, log base 10 of I over I naught. So let me get to each of these things in turn. First off, what's this decibel? This is just a symbol. It's not a unit. That just is trying to describe how loud something appears to you. But it doesn't actually have any physical dimension. Why is it decibel? Well, there's a whole history behind why it picked up a deci prefix, but anyway. This I naught is a reference intensity level. For talking about human sound perception, this is usually set at 10 to the negative 12 watts per square meter, which if you think about it, that ain't much. And what this is if you take young people who haven't heard very many loud sounds in their life and you put them in those soundproof rooms, and what you do is you start playing very, very quiet noises, and you ask them to raise their finger when they think they might have heard something. The average intensity level where the reference intensity, the average intensity where they raise their finger will be around this 10 to the negative 12 watts per square meter. There are other reference intensities that are used, but this is the one that's used for, say, sound ordinances, where they decree that a party is too loud if the cop's decibel meter reads a certain number. That'll be calibrated at 10 to the negative 12 watts per square meter for the reference intensity. The other standard out there, which you'll see with your stereos, is that for a certain prototype speaker, they will set it to be that if the hearing position is 1 meter away from this particular prototype speaker, the reference level is 1 watt per square meter from that reference speaker at 1 meter. This has the, as we'll see, if this has the deal that it's because usually the ears start hurting at about 10 watts per square meter. So a reference intensity of 1 watt per square meter, that's where you're going, oh boy, is that loud. That's getting to be like at rock concert loud. And so nobody ever wants to go any louder than that because they don't want they don't want people's ears to start hurting. So if you have a amplifier that quotes all the volumes in negative numbers, that's because the negative numbers mean it's quieter than a rock concert. And if you have positive numbers, it means it's louder than a rock concert. Because remember, if you take a log of a number less than 1, you get a negative. If you take a log of a number bigger than 1, you get a positive. And also the other thing to really, really watch out for here is that this is a base 10 log. So this is the LOG key on your calculator, not the LN key. The only two base 10 logs in physics are this sound intensity level, which is an empirical fit describing how ears hear sound, and stellar magnitudes, which turn out to be an empirical fit for how eyes perceive brightness. So go figure. In both of those empirical fits, base 10 logs were used, and so that's what shows up. Every other logarithm you will ever have in physics will be a natural log, which is the LN key on your calculator. And to make matters even more annoying, physicists usually write LOG when they mean natural log because, of course, it's always a natural log. So it's only for these two where it isn't. So at least when I write it down, I try to be super duper careful and always explicitly denote that it is a base 10 log. All right. So if seeing logarithms is giving you some bad flashbacks to algebra class, let's go ahead and just do a couple quick things to refresh our memory on how this works. So let's just start with, first off, let's take a look at my rock concert level. So for a rock concert, we have that the intensity of sound is usually on the order of about, or sorry, not a rock concert, I want to do a threshold of pain, my bad. Give me a moment here. So usually when people start to complain that they're, come on, doggone it, there we go. Usually when people start to complain that their ears are hurting, is around 10 watts per square meter. So let's figure out what the sound intensity level is that corresponds to that. So putting in the sound intensity level is going to be 10 dB times the base 10 log of I over I naught. Well, I here is going to be 10 watts per square meter, and my reference level is 10 to the negative 12 watts per square meter. Now, one thing that you always need to have happen is log is another one of those things where you need all the units inside to cancel, because I don't know what it means to say log of watt. So let's figure out what that will work out to be. So be really careful here when you're using your calculator. Remember, this 10 is the same difference as 10 to the 1. So if you want to do this without a calculator, in this one we can. Remember, 10 to the 1 divided by 10 to the negative 12. The rule is you subtract exponents if you divide. So this will be 10 to the 1 minus a negative 12, which is 13. So this will be, 10 dB times the base 10 log of 10 to the 13. Now, to refresh our memory, remember these identities. It is the case that 10 to the base 10 log of some quantity x will be equal to x. And it's also true that the base 10 log of 10 to the x is also that number x. So the logarithm is the inverse of raising the base to some power. So 10 to the x, the log of 10 to the x is x. It's just the thing that picks out the exponent. And you can, in principle, write any number as 10 to the something or other, as long as it's a positive number. It's just that you might not have a nice clean integer. But here we do. So in our example, this will be 10 dB. So this is the base 10 log of 10 to the 13. So that's just picking off the exponent on the 10. So that's 13. So 13 times 10 is 130 dB. Rock concert loud, like I mentioned, that's 1 watt per square meter. If you go ahead and do that, you'll get that. That turns out to be 120 dB. All right, let's try another one. Let's say that you were running a sound meter on something and you got the intensity level to be 30 dB, and you wanted to know what the corresponding intensity was. Okay, so we remember that the sound intensity level is 10 dB, base 10 log of I over I naught. Now the trick is we need to pull out the I from the log. So let's go ahead and do that in steps. First things first, we'll just divide through by the 10 dB. So we'll have the base 10 log of I over I naught is equal to beta over 10 dB. Cool. Now, the thing is, I want to get the I by itself, and I remember that 10 to the log of the thing is the thing. So as long as I raise 10 to both sides, that will still be an equality. So that would be giving me 10 to the base 10 log of I over I naught. And as long as that will equal 10 to the beta over 10 dB. Okay. So now I can pull out what's inside here by saying, oh wait, 10 to the log of the thing is the thing. So this is I over I naught is 10 to the beta over 10 dB. And so finally we get that the sound intensity is I naught times 10 to the beta over 10 dB. All right, now we said it was 30 dB. So let's go put in our I naught, unless you're told otherwise, it's 10 to the negative 12 watts per square meter. This will be 10 to the 30 dB over 10 dB. And even though decibels aren't properly a unit, you still feel good when they cancel. In 30 over 10, that's just 3, so that's 10 to the 3. So 10 to the 3, and remember when you multiply exponents, you multiply these, you add exponents. This is 10 to the 3 plus negative 12 gives me, 10 to the negative 9 watts per square meter. All right, let's just do one more for just what if it turns out to be the case that we don't have a nice clean exponent. So let's try one that will turn out to be below the threshold of human hearing. We'll do a sound intensity level of negative 25 dB. And we, again, want to find out what is the intensity level. Well, we can recycle the exact same result we had right here. This is why using letters is awesome. So I will just recycle the result because nothing really changed here. And just put in the new values. So again, my reference intensity is 10 to the negative 12 watts per square meter. So it'll be 10 to the negative 25 dB over 10 dB. And once again, we feel reassured seeing the dBs cancel out here. All right, so let's go and crunch this one through. For this one, we're going to need our calculator. So I'll go ahead and take my exponent here. This will be 25. We'll divide that by 10 to get 2.5. We need to change the sign to get a negative. And so now we're going to need the 10 to the x key. So 10 to the negative 2.5 is that. And then we are going to raise that, multiply that by 1 times 10 to the negative 12. Now be super duper careful here. When you do that, that's going to be 1, and then this is either an EXP or EE or E on your calculator. But you'll just put in that it's negative 12. Don't type 10 E negative 12, because then that's 10 times 10 to the negative 12, which is really 10 to the negative 11. So if you got something like 10 to the negative 12 here, you have to type 1 EXP, or that's what it is on my calculator. For yours, it's probably E or double E, and then you're minus 12. Anyway, we'll times those together, and we get that's 3.16 times 10 to the negative 15 watts per square meter, which, as I advertised, was lower than the threshold of human hearing. So that's the whole deal. If these sound intensity levels are negative, a young ear that has never been exposed to lots of heavy sound won't be able to hear it, and if it's a positive number, that same ear will. Okay. So I'll close this off by doing one more example. So let's go back to our standing in front of a subwoofer problem that we did here. I'm going to steal the figure. There it is. But now what I'm going to say is, instead of it being intensities, we're going to talk about intensity levels. And so I'll start again by saying I'm 5 meters away from the subwoofer. And so that means that here the intensity level is some level beta 1, which I don't know what it is. Now I want to know how far away should I stand so that the intensity level I hear is 20 dB less than what I had before. So to hear a drop of 20 dB. How the heck would I go about doing that? That one might seem absolutely awful. So this is basically amounting to saying that I want beta 2 minus beta 1. Beta 1 minus beta 2, because I want a drop of 20 dB. I want beta 1 minus beta 2 to be equal to 20 dB. All right, that's what that is. So what we can do is let's just, for the the grins. We'll just call this delta beta for the moment, just to make it a little easier to write. So this delta beta, well, it's not really a change in, yeah, okay, fine, sure. We'll call it delta beta anyway. So what's this going to be? It's beta 2 minus beta 1. So beta 1 minus beta 2. Beta 1 will be the base 10 log, 10 dB times the base 10 log of I1 over I naught. And similarly, this will be 10 dB times the base 10 log of I2 over I naught. Well, that doesn't sound too hopeful, but this, when you're dealing with logs, if you subtract logs, that's really dividing the insides, so this is actually a stealth scaling problem. So just another quick reminder of some identities involving logs. The log of A plus the log of B is equal to the log of A times B, and similarly the log of A minus the log of B is equal to the log of A over B. And while we're at it, just one more for the grins. The log of A to the n is equal to n log A. I'll just throw that in for some bonus content there. All right. But here, this is the one we need. Log A minus log B is the log of the quotient. So this looks awful, but it's not all's lost. So we can pull out a 10 dB from both terms, right? And what have we got? We've got the log of I1 over I naught minus the log of I2 over I naught. And now we can apply that identity. So this change in intensity will be 10 dB times the log of the quotient of the arguments. So this will be I1 over I naught divided by I2 over I naught. And at least, thankful for small favors, the over I naughts cancel, so at least we have that. Well, you might say that doesn't sound too useful, but it's a step in the right direction. We still don't know how to express the intensities, but we do remember that they're the power of the source over 4 pi r squared, right? So let's put that in. So this will be times the log of I1 will be the power of the source over 4 pi r1 squared. And this will be the power of the source over 4 pi r2 squared. Hey, check it out. So the powers will cancel and the 4 pi's will cancel. So this will leave me with (10 dB) times the base 10 log of, again, rationalizing the denominator, multiply top and bottom by r2 squared, of r2 squared over r1 squared. So that'll be 10 dB times the base 10 log of r2 over r1 quantity squared. Oh, hey, you didn't really think that was bonus content I gave you. That's another identity. The log of something to a power is the power times the log. So this will be 10 dB times 2 log base 10 of r2 over r1. So we can clean that up and make that 20 dB. So, just so we don't forget, that was delta beta equals. Well, believe it or not, we're almost home. All we have to do now is go ahead. Let's see here. I want to get R2 by itself, so let's divide through by 20 dB. So log base 10 of R2 over R1 equals delta beta over 20 dB. And now I can finally take the anti-log of both sides. So 10 to this equals 10 to that. So 10 to the log base 10 of R, well, we'll just make it explicit, 10 to the log base 10 R2 over R1. That will equal 10 to the delta beta over 20 dB. Well, 10 to the log of the thing is the thing, so it's R2 over R1, carrying that. And finally, I can times through by R1 and substitute. So R2 will equal R1 times 10 to the delta beta over 20 dB. So R2, in the problem we said R1 was 5 meters, recycling the same number as before. This will be 10 to the, hey, wasn't that nice of me to say the change was 20 dB? So that's 10 to the 1, which is 10. So 50 meters. So in order for you to notice a 20 dB drop, you have to stand 10 times farther away, which does indeed match how we actually hear things. Alrighty, so I will catch you on the flip side.